the description of sets of congruence classes, modulo some modulus, under the operation of multiplication. The appropriate algebraic setting for this kind of thing is a group. It's called a group. And a group is an object, it's a set, together with an operation on it. So the set for us is going to be the set of congruence classes, modulo whatever. The operation, okay, we're focusing on multiplication now. The operation is going to be multiplication modulo that modulus. The properties we're interested in are the four group properties. It's being closed, associative, existence of an inverse, and existence of an identity element. The identity element for multiplication, as always, and the same for multiplication modulo n, is the congruence class of 1. Okay? 1 is the identity for multiplication of numbers. However, we proved yesterday that not all of the elements will have necessarily an inverse modulo n. In theorem 4.6, we said the congruence class A modulo n has an inverse if and only if it is coprime to n. Okay? So all the ones that aren't coprime to n, we have to chuck them out in order to have a group, a nice multiplicative system. So here's an example, for instance, Z8. So Z8, we've chucked out all the even numbers, okay? Because the even numbers are not coprime to 8. Okay, so we've thrown those all out. We've left with the ones 1, 3, 5, and 7. They're coprime to 8. And they form a nice multiplicative system under multiplication modulo 8. And that's what we do, okay? Interesting cases like 5, when the modulus is prime, okay? All of the numbers less than it are coprime to it, except for 0. So 0 is the only one you have to discard when the modulus is a prime number. Okay, so you've got p minus 1 elements here, 5 minus 1, you've got the 4 elements here. When you're talking modulo 5, you've got a nice group system under multiplication modulo 5. Another example, just one we were doing with the computer last time, we formed this object here is Z15, which was the ring of integers modulo 15. This is what the multiplication table looked straight off when we include everything between 0 and 15, and lots of zeros around the place. Lots of elements don't have inverses. For instance, 6. When you scan across the row corresponding to 6, there's no 1 there. So none of these elements, when you multiply it by 6, does it ever give you the identity element back again. That's because 6 is not coprime to 15. 6 is the greatest common divisor of 3. Okay. Now when we do eliminate all those elements, just what I do down here, so when I define a new variable z15x, so this consists of all the z's for z and z15, all of everything between 0 and 14, but only if the GCD of z with 15 is equal to 1. So that is, as you can see here, just the set of things that are coprime to 15. So this new variable z15x, and then if I change this command here and type in elements equals z15x, so that means I only want the multiplication table for these elements here. So I'm chucking out all the ones that are not coprime to 15. That reduces the table somewhat. Okay, so we've lost all the multiples of 3 and all the multiples of 5. They're the ones that are not coprime. Now we have a nice group multiplication table. Okay? Every element has an inverse, because when you look across any row, you'll encounter the number 1. And that's the inverse for that element. So 11 is self-inverse. 11 times 11 is 1. Any other self-inverse number? Yeah, 4. 4 times 4 is 1. Lots of other elements are not self-inverse. For instance, 13. 13 times 7 is equal to 1. Okay. Any questions so far, just on the kind of section? Now, one reason we're doing this is because we want to be able to have a method for simplifying quotients. There's a couple of problems like this in the coursework. If we're faced with a, sorry, what's simplified? I think I said quotients, but I meant powers, okay? Exponents. So if we've got an expression a to the power b, we want to understand how to simplify it modulo n. Okay? The one way we can simplify it is we can replace a with a simpler element modulo n. So if we know that there's some other element a prime smaller than a, which is congruent to a modulo n, then a to the power b will be congruent to a prime to the power b. So that's one way to simplify powers, okay? But what we want to arrive at now is a way to simplify the exponent, okay? Because if the exponent is large, we can't hope to evaluate this integer power exactly. It's got a large exponent because they blow up in value. So we want to know how to simplify the exponent. And we've already looked at a few examples to do with that. And it's to do with the cycle of elements that the power of the base goes through inside the group modulo n. Okay? So it's that topic that we're going to investigate further. Okay, we're introducing this new object called the Euler totient function. It's traditionally written using the Greek letter phi. Indeed, it's sometimes called the Euler phi function, because phi is almost universally used as the letter to denote the function. So phi of n, one way quite simply of writing what it is phi of n is the size. Phi of n is the size of the reduced residue system modulo n. Okay, so Znx, Zn times multiplication is the set of residue classes, set of congruence classes of integers modulo n that are co-prime to n. They're the ones that form the group. Phi of n, quite simply, is defined as the size of this. So in other words, phi of n is the number of integers a between 1 and n that are co-prime to n. That's the size of this group. Okay. Now the reason we're so interested in the size of the group, well, knowing what the size of the group is one measure of the group, is one way of describing what kind of group this is. A small group is an large group. But the other reason we're interested in the size of the group is that it's quite connected. I'll do this on your better. So it's the Euler totient function phi of n. It's defined to be the size Znx, i.e. it's equal to the number of integers a in the range 1 between n, such that the GCD of a and n is equal to 1. Okay, this is our Euler totient function. What's its connection to exponents? Okay. The reason the size of a group is important is because of what's known as Lagranges theorem. So Lagranges theorem is a theorem about group theory. We're going to take something from it here, although we will prove the results we're taking from it from the ground up in the setting of modular multiplication. But what Lagrange's theorem says is for a finite group G, size n, if G, little g is any element from the group, when you raise g to that power, when you raise g to the power n, okay, this isn't exactly what Lagrange's theorem says, but this is the aspect of it that we want to say. When you raise that element to the power n, Now, what does that mean? That means you multiply the element G with itself n times. There are n copies of G here, all multiplied together. So if you have a binary operation, you can define positive integer powers of it. G to the n just means G multiplied by itself n times. What we get from Lagrange's theorem, as I said, it's not exactly Lagrange's theorem, but it's one aspect of it, is that this is equal to the identity element. Equal to E, the identity element. The identity element in the group. So in the context, our context, inside these groups of congruence classes of integers modulo n under multiplication modulo n, this becomes Euler's theorem. And Euler's theorem says if GCD of A and n is 1, so if A is coprime to 1, sorry, if A is coprime to n, i.e. the equivalence class of A, the congruence class of A is an element of Zn times, so A is an element of the multiplicative, the group of congruence classes under multiplication modulo n, then A to the power of the size of the group. Now, the size of the group is this Euler totient function. This will be equal to the identity element. So in other words, A to the power 5n will be congruent to 1 modulo n. And it's this fact which will allow us to simplify an arbitrary power of A. Okay? So this is Euler's theorem here. So you can see, in one way you can justify Euler's theorem because it's a special case of Lagrange's theorem. So we can appeal to group theory. But that's a bit unsatisfying because we haven't proved it for ourselves. But so that's how I'm explaining it for the moment. But we will be able to prove Euler's theorem ourselves within number theory, just using the tools that we've developed so far. But first of all, to show you what it's used for. So how does this help us simplify an arbitrary power of A? So if we seek A to the power B, what I can do is I can divide B by 5n. And I'll find that B is equal to some multiple of 5n plus some remainder. And the small integer remainder will be between 0 but strictly less than 5n. 5n, remember, is the size of this group, the number of integers between 1 and n that are coprime to n. If I integer divide b by 5n, if I know 5n, so I can do this integer division, then a to the power b, which is equal to a to the power q 5n plus r. Okay, just using rules of indices, this is a to the 5n to the power q multiplied by a to the r. It's just basic algebra, basic properties of exponents. This is, you split up the sum of the exponents, so it becomes a to that power times a to the power r. But then this product of exponents, so it becomes a to the power of one of them to the power of the other one. But then once I consider the congruence class of this, so 3 lines now, these are equations, but now I'm going through a congruence. Euler's theorem tells me that a to the phi n is congruent to 1. So this thing is now congruent to 1 to the power q times a to the r, but 1 to the power q, I can simply drop that. This is just congruent to a to the r. So no matter how large the initial exponent b might be, if I know phi of n, if I know the size of this multiplicative group under multiplication modulo n, I can basically shrink down this large exponent and just deal with the remainder left after I integer divide it by phi of n, okay? And that remainder cannot get any worse than phi of n minus 1. So instead of dealing with the potentially unmanageably large integer a to the power b, I can deal with the much better one, a to the power r. Okay? R can only get so bad. Okay? Whereas b could be arbitrarily bad at the start. In terms of the coursework, b could be as bad as an 8-digit number, like your ID number that you're asked to deal with in multiple. So knowing phi of n, knowing the size of this group, allows us to break down the exponents. So that's why we're so interested in phi of n. So this object here is a lot easier to deal with compared to this object here. Okay, because that b could be huge, but the r can only get so bad. Okay, the r is contained. Okay. Everybody feel that and appreciate why we're going after this phi. Of course, in order, if I'm faced with a to the power b, in order to find the r, I have to know what phi of n is. I have to be able to do the integer division. Okay. So this is why, this is one of the reasons why, this is why we might be interested in phi of n. Okay, any questions so far? Okay, so we're interested in phi of n, so that's why there's a whole chapter called chapter 5, Euler's totient function. So what I'm going to do now is give a kind of brief overview of what's in chapter 5 and jump to the end of it and prove the nice, interesting result at the end, or prove a nice, interesting result at the end. And we'll return to chapter 5 in coming lectures and work through the substantial, well, the somewhat technical nature of the results. Okay, so chapter 5 seeks to describe this Euler totient phi of n. Now, in one case, we already know what it is. It's the size of this group. And as I said in the notes already, it's the number of integers a between 1 and n, which are coprime to n. That's what it is. So we have the definition of it. If you give me an n, I can sit down and look at all the integers between 1 and n, work out which of them are coprime to n. Okay. However, it's not a very satisfactory definition. If you might give me a very large number n. Okay, so there'll be an awful lot of candidates A in this range. Do I have to test each one to see if it's coprime to n? Just count them all up, and then at the end of that process, I'll know what phi of n is? Well, yeah, I will. But potentially that might take very long. And also, I don't know ahead of time, like, there's nothing in here which is saying, well, if n is of this type, then the value will look like this, and if n is of another type, the value will look like something else. There's not a lot we can get from that definition as it stands. Okay. So a better view of phi is provided. What I mean, like we're introducing these results just kind of setting them in context, looking at the interesting result. But a better view of it is provided by Theorem 5.1. And this is another way of, what have I used, alphas or? I'll use So what am I talking about here? If n is equal to this, what's this? This is our nice canonical form of an integer, the prime factorization of n. So if this thing here, if n equals this, is the prime factorization of n. So look, in other words, I've got a set of distinct prime numbers, p1, p2, p3, to the last one, pr. These are all the different distinct prime numbers that feature, that divide n. And here I see them also raised to various powers, ai. And you multiply all those things together. Remember, that's what the capital pi is, the product operator. Multiply all those powers of primes together, you get n. Okay? So that's the prime factorization of n. That's the nice canonical way of thinking of an integer in number theory, in some sense. Well, what Theorem 5.1 is it gives a really handy, beautiful, relatively straightforward to understand formula for what phi of n is based on the information here. Okay? It's not quite a prime factorization of n, but because there's some extra factors in there. But it's very much an expression like this. And the expression is, well, it's a product over the same range, product of the same prime numbers pi, but this time they're raised to a power 1 less than they were before. So you got to reduce the power by 1 for over each prime. And you also have an extra factor thrown in there. The extra factor thrown in is pi minus 1. Okay, so there's a pair of brackets around there. So we're taking the product of all these green brackets. Okay? Each green bracket depends on the index I. Each green bracket talks about one of the primes that feature in the prime factorization of n. And it's that same prime raised to a power 1 less than it was before. And you've got an extra factor of pi minus 1. So for most primes, this is an even number. This will be a composite number, an even number. Okay, because most large primes, 1 less than it is an even number. Okay. So we'll check this. Okay. So this is a nice, easily understood, well, manageable formula. Manageable formula for phi. It's nice. If you know n, think of it, if you know n in a multiplicative way, see, if you have all this data here, you know about n in a multiplicative way. Know how it breaks down as a product of prime powers. Then you have a similar viewpoint on phi of n. You know phi of n in a nice multiplicative way. This isn't exactly a prime factorization. All these things here are powers of primes, but these things aren't. These are, in general, composite numbers here. Okay? So you do have the odd composite number thrown into the product. Okay? We could just do a quick example of this, e.g., what's phi of 15? Well, 15, its prime factorization is nice and simple, simply 3 by 5. So P1 is 3, P2 is 5, and A1 is 1, and A2 is 1. It's 2 primes, both raised to the power 1. So according to this rule, I have to take the product over these 2 prime numbers. I have each prime number, but I raise it to a power 1 less than it was before. Well, here I have 3 to the power 1. If I raise it to a power 1 less, I'm raising it to the power 0. So 3 to the power 0, so that's 1. So effectively, the 3 disappears. But I get this extra factor here, 3 minus 1, otherwise known as 2. Okay, that's the first prime. And then, well, I continue on to the second one, taking the product. So I multiply it by 5, raised to the power 1 less than it was before, multiplied by 5 minus 1, 4. Yeah? So it's 8. Yeah? So there are 8 things that are coprime to 15, 8 congruence classes modulo 15 that are coprime. Which agrees with what we see 15 was that example I was showing you on the computer, which agrees with what we found as Z15X, consisting of the congruence class of 1, 2, not 3, 4, not 5, not 6, 7, 8, not 9, not 10, but 11, not 12, so it's got a 3 in it, 13, 14. 8 things there? Should be 1, 2, 3, 4, 5, 6, 7, 8. Everything else that I've skipped over is not coprime to 15. Yes. These across here. So I was following this formula here. So this view of 15 is 3 by 5. This is my example of this up here. So you have to understand. So it's capital pi. So that's a product operator. So I'm taking the product of expressions like this, which is a prime number to some power. Well, here, yeah, so I'm taking a product over 2 prime numbers. So if you want to match this expression to this one up here, you've got r equals 2, and p1 is 3, and p2 is 5. a1 is 1, and a2, the power of 5, is also 1. Okay? And then I'm feeding all of that into this formula here for phi of n. So phi 15. So again, it's a product from I equals 1 up to r. So it's a product from I equals 1 up to 2. So it's something to do with the 3 multiplied by something to do with the 5. What is the something? It's the prime number raised to a power 1 less than it was. So first I take 3 and I raise it to a power 1 less than it was. Well, it was to the power 1 here. So it becomes to the power 0. But then you've got this extra factor, which is 1 less than the prime. So still focused on 3, I've got this 2 here. So this 2 is this bracket pi minus 1 for the case 3. So that's the stuff to do with the prime 3, but then I've got the stuff to do with the prime 5. Again, 5 to the power 0, 5 to the power 1 less than it was before, and also multiplied by 1 less than 5. Multiplied by 4. Can you see that? So this is an instance of this general formula. Okay. So yeah, you've got to be confident in working with that product operator and working with those expressions with indices and so on. Okay, and theorem 5.1 is the whole result of chapter 5. All the other results are there as a build-up to this. Okay. All the other results in chapter 5 build towards the proof. Build towards the proof of theorem 5.1. It's a really nice formula to have. Okay, but you can't just take my word for it. We've got to prove it and know that it's true. Okay? And once we know this, then it gives us a good way to know the value of phi of n given any n. And that in turn will allow us to simplify these powers of a number. Now what we're going to finish with, what we're going to end with, is what's known as Fermat's little theorem. Everybody knows what Fermat's last theorem is, was that very hard problem which was only relatively recently solved. about there existing no Fermat triples for any power bigger than 2. But there's this other result called Fermat's triple theorem. Okay, so this is at the end of chapter 5. It's the corollary to Euler's theorem. And this says if P is a prime and P does not divide A, or another way to think about that is the greatest common divisor of A and P is 1. Then A to the power P minus 1 is congruent to 1 modulo P. Okay? So we know that any integer which is not divisible by P, when you raise it to the power P minus 1, you get 1 modulo P. So as I say, this can be justified as a consequence as coming from Lagranges theorem in group theory. But that's a much more general result, speaking about the whole, any kind of group. Here we're just dealing with these specific groups. So we perhaps prefer today to see an argument completely within the language, completely within the context of this group. So we need some way of building this power, A to the power P minus 1, building it in a nice way. Okay? So we consider the P minus 1 standard residues. What do I mean there? There I mean the standard representatives of the congruence classes modulo P. But we're not considering 0. 0 is not in the game. 0 is not interesting from a multiplicative standpoint. If you multiply anything by 0, just immediately 0. 0 kills them. Okay? But we consider these ones. And multiply them all by A. So you've got A, 2A, 3A, 3 times, P minus 1 times A. And what we're going to do is multiply them all together. And then we'll have A times A times A times A. We'll have A to the power of P minus 1. And that'll be multiplied by P minus 1 factorial. You got 1 times 2 times 3 times 4 all the way to P minus 1. But the first thing we want to do is understand that the congruence class is represented by these are all of these ones. Okay. So the congruence classes represented by A times J, where J is between 1 and P minus 1, are all of the congruence classes represented, I'm spelling represented each time, it's okay. Represented by J. 1 less than or equal to J, less than or equal to P minus 1. Here we've got J for every J between 1 and P minus 1. Here we've got A times J for every J between 1 and P minus 1. But the claim is, you look at all the congruence classes represented by these P minus 1 numbers here. It's all of these ones. You don't miss any out. Okay? So the proof of this, the proof needed for this claim is if, on the contrary, so if this wasn't the case, then we'd have to have A times J1 being congruent to A times J2. So if it was the case that these didn't represent all of these ones, then the only way that could happen is if two of these were congruent to the same thing up here. Okay, remember, everything is congruent to one of these. So if two of these were congruent to the one thing up here, then you'd have aj1 congruent to aj2 modulo p. But what can I do here? I know A is coprime to P. And we proved a lemma here that you can cancel factors from both sides of a congruence if you know that the factor is coprime to the modulus. So that implies that J1 is in fact congruent to J2 modulo P. But you see, all of these things are different congruence classes. Okay? So this can never happen. J1, taking two of these J's, they can never be congruent to one another. Okay? Because they're chosen to be from different congruence classes modulo P. These are all the standard residues mod P. So, with that little proof over, so I know now that the P minus 1 integers here, if I look at all their congruence classes, it's all of these congruence classes here, 1 through P minus 1. So when I multiply, let's use J since I've been using J's. When I multiply AJ, when I multiply all the AJ's together, where J is running from 1 through P minus 1, what I'm doing is multiplying together all of these. That tells me that it's congruent to multiplying together all of these ones. So at the end of the day, I'm just taking this bunch of congruence classes, and here I might have them written down in a different order. Okay, and just multiplying them all together again. Okay, so it's the same overall collection of congruence classes. When you multiply together all the AJ's, it's the same as multiplying the same, meaning congruent modulo P, multiplying together all the J's. But now, what's this equivalent to? Well, you see, you've got the same factor A here in each factor in this product. So I've got A to the power P minus 1. So there's P minus 1 factors there. And there's an A in each of them. So I've got A to the power P minus 1. Then I'm multiplying 1 times 2, I'm multiplying all the J's. 1 times 2 times 3 times 4, all the way up to P minus 1. So we know that by a better name. It's P minus 1 factorial. Yeah. So that's congruent to, and again, here on the right, I have P minus 1 factorial. But now this is nice. Lo and behold, here I've got the same factor on both sides. So what I want to do is strike it out, to cancel it out, to simplify. Am I allowed to do it? What tells me if I'm allowed to do it? Yeah, if the factor you're going to strike out, if it's coprime to the modulus, is P minus 1 factorial, is it coprime to P?
Yeah.
Why?
Because it contains P.
Because?
It contains P. No, it doesn't.
If it contained P, then it wouldn't be coprime. It would have P as a common factor. See, I want it to be coprime.
Because P is prime.
Yeah. What divisors does P have? One in itself. So the only possibility for a common divisor with P is 1 or P. And is P made up here and multiplying these numbers together? No, it can't, because, as you say, P is a prime number. You can never magic P up by multiplying together small things. If P was just some number n, and I was taking a factorial of something less than n, then yeah, I could manufacture n stuff less than. But p is a prime number. You can't do that. So the factorial of something less than p has to be coprime to p. So that factor there is coprime to p. So yeah, I can strike it out. So that's true if and only if a to the p minus 1 is congruent to 1 modulo p, as required, which is the thing we were trying to prove. And that's true because p minus 1 factorial is coprime to p. Because p is a prime. The primus of p is right here. P is prime. So what? Hey ho, what have we done? We've done this. Any number which started off being coprime to p, so if it was in this multiplicative system Zp, when you raise it to the power of p minus 1, we know that that's congruent to 1. So we can use this as a base to simplify powers of a modulo p. So whenever you see that power, it's effectively not there because it's just a factor of 1. Okay. It can be seen as coming from this very general deep result in group theory, which applies to a much wider range of mathematical structures, but you could also see it as just a number theory type result here, just proved using techniques of congruency. So an exercise for you, I won't see you now again until next Monday. We'll have a lecture and then tutorials the following Friday. The exercise for you is to provide a similar, it's somewhat similar, quite similar, not precisely the same, but cousin to this, provide a similar number theory or number theoretic proof of Euler's theorem. Namely that a to the power of phi of n is congruent to 1 modulo n. So this is much more general. Here we don't have a prime number. It could just be any old modulus. Of course, what's phi of p? Phi of p is p minus 1. So Fermat's little theorem is a special case of Euler's theorem. But along very much similar lines, similar approach, you should try and construct the proof of Euler's theorem. And using that same machinery there. You don't mention factorial so much, but you still use the same concept of multiplying everything together. Okay, so I'll see you next week.